Hello dear students, welcome to Pen and Paper Chemistry on YouTube. The topic that we are taking up now is properties of benzene, and this is part 1 of a set of videos on this topic. Properties of benzene can be classified into 4 categories. We have the substitution reactions, addition reactions, oxidation reactions and coupling reactions. And as you can clearly see, I have drawn them out in the form of a flow chart, an easy to follow as well as remember flow chart. So, why don't you do one thing? Why don't you grab a big piece of paper, maybe an A4 size paper, some sketch pens, so that you can draw this chart with me and you will have some material which is easy to remember and recall. Right? And don't forget your notebook as well, because we will be writing reactions based on this flow chart, and that will be a good practice for you, right? So pause the video, get all these things in one place, a paper, sketch pens and your notebook. So you can draw this flow chart, and what we are going to do is we are further going to divide each of these into smaller branches, right? The property that we are taking up today in this lesson is substitution reactions. So first of all, for those who are not clear with the concept of substitution reactions, just a quick touch base on substitution. That is, substitution reaction means when an atom or group is replaced by another atom or group. So, for example, we have an alkyl halide, the halogen atom over here is replaced by Y, R, Y, and X is released. This is an example of a substitution reaction, just like you have a substitute teacher in the class. So, an atom or group replaced by another atom or group. Now, what is this group which is replacing the original atom or group decides whether we call it as nucleophilic, free radical or electrophilic substitution. So, if the incoming group is a nucleophile, nucleus loving, it is called as nucleophilic substitution. Incoming group is a free radical, then it is free radical substitution. Incoming group is electrophile, it is called as electrophilic substitution. Now, out of these 3 categories, what kind of reactions are undergone by aromatic compounds is what we are going to see now. Before we go on to decide or see what kind of substitution reactions are there, we have to understand the structure of aromatic compounds, and specifically I am going to stick to benzene, the first basic aromatic compound. Now, if you notice over here in the case of benzene, what do you have is a 6 carbon hexagonal ring, and there are 3 double bonds, correct? 3 double bond means there are 3 pi bonds over here. Something interesting that is observed. Pi bond means the electron cloud is above and below the nucleus, right? This is how the pi bond overlap takes place, correct? Let me remove the line from here. So, both the lobes are overlapping. Now, the next thing, we are going to talk about a nice game that you usually play, the monkey in the middle, right? Here what happens is, we have these 2 children playing. They have a ball in between them. I want that ball, but what happens is, when I go near the student, he tosses the ball to the second child. Go to the second child, he tosses it back to the first one. So, I am left hunting for that ball, correct? Okay. Let us say if instead of 2 students, there are 3 of them. There are 3 children playing, and there's this monkey in the middle. Let's draw a monkey in the middle here. So this is my monkey in the middle. Tries to get the ball from the first child, he tosses it to the second. Goes to the second child, he tosses it to the third. So what is happening? Now the ball or the object is being tossed around between one to the second to the third child. So this is scenario number 2. So we had one where the ball was being tossed between 2 children. We have the second scenario where the ball is being tossed between 3 children. And if you notice, I have a third figure ready for you where the ball is being tossed amongst 4 children. See, the possibility of the ball going anywhere between the 4 children is very, very high. Now, what are the chances out of 1, 2, 3? In which case would it be easy for me to get this ball from the children? Case number 1, 2 or 3? Absolutely, it will be easiest in the case of 1 and most difficult in the case of 3 because the number of children involved is higher. The number of probabilities or possibilities of the ball being tossed around are also high. Now, because of these possibilities here, the chances of the ball remaining with this group are very, very high. And this is something which we correlate to what we call as resonance. So, in the case of benzene, what happens here is, this is the structure of benzene as we drew earlier as well. Now, in this structure of benzene, all the red lines that you see are nothing but sigma bonds between the carbon atoms. So, it is something like this. The vertices are being occupied by the carbon atoms which are forming sigma bonds with the next available carbon atom with the adjacent carbon atom. So, all the red lines that you see over here are nothing but sigma bonds. Similarly, each carbon atom is also forming a sigma bond with the hydrogen atom over here, right? Now, we've got one bond, we've got the second bond, we've got the third bond here for each of the carbon atoms. But we know about the tetravalency of carbon, carbon displaying a valency of 4. So, what about the 4th valency? Now, in order to form the 4th bond, what do we have over here is, this is the p orbital which is unhybridized, correct, which I am drawing in yellow. The possibility of a pi bond between carbon number 1 and carbon number 2, between this and this, is the same as between carbon number 2 and carbon number 3. Earlier what was said was that they are forming a pi bond like this between carbon number 1 and 2, carbon number 3 and 4, right, both the lobes overlapping, and carbon number 5 and 6. But what is there is equal probability of a bond formation between carbon number 2 and 3 as well, right? So, let us show it by like this. Oh, look at that, there is a beautiful pattern developing over here. Do we notice? So, what happens over here is the electron cloud is actually distributed. So, the electron cloud, what happens is, it is not confined to any 2 carbon atoms. It is, yes, let's convert all the dots also into solid lines. And what do we have over here? We've got a ring of electron cloud above and below the plane of the benzene ring. So, you notice over here, okay, wait, let me. So, now what we've got over here is we've got a benzene ring, and benzene ring, all the sigma bonds are there. So, I am drawing it in white, and interestingly, there's a ring of electron cloud above this ring, right, and below this ring, making it what? Yes, it makes it electron rich. And because now, so that means this is electron rich above and below the plane of the benzene ring, just like your sandwich, correct? So, there is bread above it, there is bread below it, and in between are your fillings, correct? So, what we've got over here is we've got electron rich benzene ring, which is above, the electron cloud is above and below the ring. Now, because it is electron rich, it is going to attract something which loves electrons, and loves electrons means it is phile. That's the word we used, remember, for loving. And what does it love? It loves something which needs electrons. So, it loves electrophiles. Electrophile is one word. So, electron loving species. It is going to attract something which is electron loving towards itself. But that something which comes towards it, because it loves electrons, is very smart. You know what it's going to do? Let's see. So, this electron loving species, it comes to benzene. Now, first of all, because we've got this ring above and below, instead of drawing our pi bonds like this, how do we represent benzene is we indicate it by this dotted circle, because now this ring of electrons is very much like these children who were tossing the ball, in between them. So, 4 children, right? The possibility of the ball staying here is very high. Same thing is happening over here. Now, instead of 4, there are 6 children who are tossing the ball between each other. So, the possibility of that ball remaining in this circle is very, very high. So, despite the fact that it has 3 double bonds, benzene does not undergo addition reactions easily. Yes, it doesn't. Although we in the flowchart we have written addition reactions, but they are not easy to come by. You will see when we write the addition reactions. And in order to denote the electron cloud, we usually put a dotted circle inside it. You will also find in many places written like this, which is equally acceptable. This denotes the electron cloud ring. So, what happens over here? In this benzene ring, because it is going to attract species which are electron loving. So, what kind of species are electron loving? Which will have positive charge on them. It calls them, come, I have a big supply of electrons, come to me. Okay, they come, but they are very smart, because they have a positive charge on them. They will make the benzene ring very unstable, right? So, this needs to get rid of the positive charge, and because there is a little guest at home, they say, okay, Mr. Hydrogen, you need to leave from here, because we need to accommodate X, and hydrogen from the benzene ring is removed. For those, sometimes we are lost. Where is this hydrogen coming from? That is what used to happen with me, sometimes totally. This is it. You see the structure of benzene, what we are drawing as a ring. Yes, yes, it happens. Honestly, it used to happen with me sometimes. Like, where's this hydrogen coming from? I'm only seeing a ring. So, just visualize the benzene that you're drawing is actually this. So, what happens is the hydrogen gets pushed off from one of the carbon atoms. It has to accommodate and leave out, go out actually in order to accommodate X. So, what has happened? One atom or group is replaced by another atom or group. So, it is a substitution reaction. The new group which has come is an electrophile, right, electron loving. Hence, the name electrophilic substitution reactions, which is the most common form of substitution reactions in aromatic compounds, or specifically, as I said, I am talking about benzene at present, not to confuse you too much. Now, the various categories of these electrophilic substitutions, the flow chart, the various categories of substitution reactions. We've got, yes, the first one is halogenation. Halogenation means, yes, very good, replacement by a halogen. And these we will categorize further as fluorination, chlorination, bromination, iodination, right? The 4 halogens that we have done. Now, fluorination would be replacement by F2. But if you recall, we had done in the case of alkanes also, these reactions are quite vigorous. So, better avoid them. Why? Take the tension, right? Next, we've got chlorination, that means replacement by chlorine. What are the conditions of that reaction? Yes, we need something to carry chlorine to the benzene ring, because chlorine is a gas, right? It will just fly all around. So, we need something which is called as halogen carriers, right? Bromination, replacement by bromine. Iodination, replacement by iodine. Nitration, replacement by NO2 group. Sulfonation, replacement by SO3H group. Alkylation, replacement by R positive. Acylation, replacement by RCO group, right? These are the major 5 categories of substitution reactions that we are going to study under benzene, and specifically the other other aromatic compounds as well. Now, let me give you a challenge. If you've already done this topic and you want to revise, okay, you want to check how much of it you remember, why don't you try writing these reactions? Try them. You see, organic chemistry is not just about watching 10 videos, 20 videos, 100 videos. You can watch as many videos as you want, but unless you write when you are understanding, your efforts, the time and energy that you will spend will not be worth it. That is why the name of the channel, I changed the name of the channel to Pen and Paper Chemistry, just as a reminder that you need to have your pen and paper with you. My God, you didn't have a pen and paper with you all this while? That's not done. Please pause the video, get a pen and paper. And well done to those who already have them with you. I hope you are writing the points as well. Write. It is very, very essential. What do you have to do next? Revise. Once you have the flow chart, bring it into your habit to read the flow chart for a particular compound. You can't read all flow charts every day. No, there's no point. You have other subjects as well to do. So, I don't expect you to do that. Keep one topic for 4 days, 5 days, or even a week. Revise the flow chart of that particular topic every day in order to embed the equations. And the third important trick, the reason I am able to teach chemistry is, yes, to teach this topic to somebody who needs it, teach this topic to a classmate, send it as a small video explaining what you have learned, or if you don't have a classmate, why don't you sit in front of the mirror and teach yourself? Become your own teacher, but write, not verbally alone. Write these reactions, and you will find that while writing itself, there are so many doubts that come to our mind. Okay, for example, I will write H and E, then I'll get confused. Where does the positive go? Is it here, or here, or here, or here? Oh, there are so many confusions. Just a small plus sign is so confusing. So teach to yourself, teach to one of your parents, ask your mother or father to just sit beside you. As a student, become a teacher, and I am telling you, you will fall in love with chemistry. You will overcome your phobia in no time. 3 easy tricks to learn chemistry. Now, what happens over here when benzene is approached by a reagent? The reagent has 2 parts, the electrophilic and the nucleophilic part. As explained earlier, the electrophile approaches the benzene ring. Now, what I will do is, I will write the ring like pi bonds over here. Oh, look at the structure that I have drawn, it's awful. Now, the electron cloud from the benzene ring, it tells the electrophile part of this reagent, says, come, I have electrons, okay. So, it shows these electrons to E positive. So, what happens over here is, E positive gets attracted to the benzene ring. But oh, what have I done over here? Look at that. This electron cloud is already used up in forming the bond with E positive. So, in other words, the double bond over here is already gone, right? So, we will have a shortage of electrons over here. That's a +1 charge, formal charge on the carbon. The other 2 bonds are remaining untouched. Correct? Next. Now, this carbon says, oh my God, I am short of electrons, I need help. Okay, it pulls the electrons from the pi bond of the next bond. So, with the result, we will have a double bond over here. This double bond is still untouched, okay, nothing has happened to it, it is staying aloof. But what happens, oh my God, to this carbon? Let me number these carbons. So, 1, 2, 3, 4, 5 and 6. Carbon number 4 says, oh my God, I am short of electrons now, I have got positive charge, I need help. Give me back my electrons. So, if it is able to pull these electrons back, we will have this same structure 1, correct? But there is another option for it. What is that option? Let's see. Yes, you got it right. It can pull the electrons from here as well. So, with the result, we get a double bond, whereas carbon number 5 and 6 are adamant. They say, no, we are going to stick to the double bond. With the result, now carbon number 2 gets a positive charge. So, if you notice all these 3 structures, structure number 1, 2 and 3, the number of atoms, the total charge on the molecule is the same. They are called as the canonical structures, and we are going to denote them by this double headed arrow, the different resonating forms. Overall, the resonance hybrid, in other words, what I have got over here is, in the benzene ring, there is a positive charge on the ring, and on the same carbon is having hydrogen and E attached. Oh, this is heavy. carrying a positive charge all the time, afraid that something negative will come and destroy me. It's a heavy feeling, right? So the nucleophile says, okay, don't worry, I'll help you out with this. I'll give my electrons to your H and let me rid you of this load, and E remains here in place. So the electrophile very smartly has replaced the hydrogen from here and formed a new product. This is our electrophilic substitution reaction mechanism. I have discussed this as a separate video as well. In case you are not able to understand, please visit the lesson electrophilic substitution. It will give you a good practice of the different substitution reactions as well. Okay? And you know, these structures, they are quite confusing at times unless, as I said earlier, you write or you draw them yourself, draw them. I have told tricks also in that video, have a look. Now, how are these or what are these electrophiles depends upon what reaction we are talking about. So, if it is a halogenation reaction, our electrophile will be X positive. So, Cl positive, Br positive, I positive. It is a nitration reaction, then it is an NO2 positive. And how are these generated? Let us see that as well further on. There you go, the flow chart, the golden thing that we have been talking about all the while. Now, where you had drawn your earlier flow chart, in this flow chart, now add this flow chart part that I have shown you just now. So, fluorination, as I said earlier, it is a vigorous reaction. We won't bother ourselves about it. Unless your syllabus specifically specifies, you can go ahead with the mechanism. Chlorination is done in the presence of halogen carriers, which are nothing but Lewis acids. What do is they help to generate the chloronium ion, Cl positive. They are called as halogen carriers. They help to generate Cl positive, which is carried to the benzene ring. Now, chlorine is a ring activating group. That means, it's ring deactivating, but what can happen is under the conditions of the reaction, it is able to cause further substitution resulting in the dichloro product. So, you have 1,2-dichlorobenzene or 1,2,3,4, 1,4-dichlorobenzene. This first one is also called as orthochlorobenzene, orthodichlorobenzene, and this one is also called as paradichlorobenzene. Unclear about ortho meta para? There's separate video under the directive influence of substituents. Please visit that. Bromination again is exactly same as chlorination, except like FeCl3 will take FeBr3. So, we don't get a mixture of the halogen derivatives. Iodination, recall the reactions which we did in alkanes. Reaction with iodine requires the presence of oxidizing agents so that it removes the HI formed during the course of the reaction. So, this HI gets oxidized and the reaction does not go in the backward direction. Nitration, in the presence of concentrated HNO3 and concentrated H2SO4 less than 60 degrees Celsius, nitro group is introduced. Now, NO2 group is ring deactivating. The ring is not ready for further substitution, and if it does happen under extreme conditions like 100 degrees Celsius, the substitution takes place at the meta position. Let me just clear your doubt regarding ortho, meta, para in short, although as I said there is a separate video on this. So, we will have a group which is already present, the positions which are adjacent to it. So, position number 1, these are called as the ortho positions. Now, 2 positions next to it. So, 2, 2. These are the meta positions. 3 positions next to it. 1, 2, 3. 1, 2, 3. Oh, these are overlapping, right? There is only one para position. So, ortho, meta and para. Usually the ring activating groups will cause substitution in the ortho and para position, and the ring deactivating groups will direct it in the meta position. But this is, as I said, usual. This is not the rule of the thumb. Okay, I am just giving you an idea so that you are able to remember. So, you will be able to recall. So, if you have a group which is having electrons which it can release to the benzene ring, it will cause ortho-para substitution, whereas if it withdraws electrons from the benzene ring. So, for example, we have NO2, CHO, COOH. Now, these kind of groups, because they withdraw electrons from the benzene ring, usually cause meta substitution and they are ring deactivating. That is in short. Please visit the video on the under the heading directive influence of substituents in order to understand more fundamentals, right. So, it is going to give us the dinitro product and further under very extreme conditions trinitro product. Sulfonation is using concentrated H2SO4 at 100 degrees Celsius, or more specifically we use oleum, the fuming sulfuric acid. And as you can see, it is only the mono-substituted product. Friedel-Crafts alkylation, Friedel-Crafts acylation. Interestingly, in most of the textbooks, you will find the catalyst anhydrous aluminium chloride. Very easy to remember, you know. Most of the time in the exams also, you will find the catalyst anhydrous aluminium chloride AlCl3 for FC reactions, but do not get confused, there are other Lewis acids as well which can act as catalyst for this reaction. Alkylation, replacement by alkyl group. Acylation, replacement by acyl group. Alkyl comes from alkanes, acyl comes from acetic acid. If you want, I can, you know, maybe magnify this flow chart for you to copy easily. Go ahead, have a look at this. Does it help? Once you've written, you can pause the video, note it down carefully where it is I2, FeCl3, AlCl3, just see carefully. Okay. Let me bring it down to nitration now for you in case you want to copy, in case you want to note down. You can always make your own flow chart as well. And you know, interestingly, you know, for all the substitution reactions, I have used the red color. You know, see over here. So, when I close my eyes, I am able to relate with color. It is easy to remember. Are we done? Have we written it down? Have we drawn the flow chart? Go ahead, we have got Friedel-Crafts acylation over here. Go ahead, note down the reagents. Fuming sulfuric acid is also called as oleum. That sulfur trioxide passed through H2SO4. We will write the reaction mechanisms of this. Okay, let us get going. So, the first reaction, substitution by halogens, also called as halogenation, right. Fluorination is vigorous. Chlorination, how do we get the chloronium ion? See the halogen carrier? Cl, Cl, we know that they are equally electronegative, but in the presence of FeCl3, there we go, positive and negative. FeCl4 negative and Cl positive. I repeat, the mechanism details are there in a separate video. I don't want to overload you with information. We are concentrating on the reactions at present. So what happens over here? Yes, substitution in the benzene ring and Cl. So we have the chlorobenzene as the product. Go on, carry out the second step of the reaction, and what will we get? Let me bring it down and write it over here. So you'll have the dichloro product, and although it is electron withdrawing group, but at the same time it has lone pair of electrons. So it causes ortho-para substitution, correct? So we will have the ortho-dichlorobenzene and para-dichlorobenzene. Don't forget the conditions of the reaction because you need them. Absolutely, yes, you need them for the bromination reaction. So go ahead, write bromination reaction, maybe the step of the reaction and the equation. I want you to write it, pause the video, make your notes complete because they are going to come in very, very handy when you revise for your exams and when you are not allowed to use your mobile. Iodination, replacement by iodine. This is done using an oxidizing agent. Why? Because replacement with iodine generates HI, which may cause the reaction to proceed in the backward direction. The oxidizing agent like concentrated HNO3, hydrogen peroxide, etc., they will convert the HI to water and iodine. Come on, boss, don't mess around with the thing. Move off from here. Let's move you out so we can use the iodine. There we go. Got it? Next, have you written the reactions? That's great. Nitration, replacement by NO2 group. How do we generate the electrophile? We always carry out this reaction in the presence of concentrated H2SO4. So, concentrated HNO3 acts as a base, concentrated H2SO4 acts as an acid, giving its hydrogen. So, what happens over here is base means HONO2, right? Acid means HHOSO4, correct? So, there we go, HSO4 negative, NO2 positive, and of course, there is water, so H3O positive, correct? So, NO2 positive over here acts as the correct electrophile. So, positive, negative, and what do we get over here? Replacement by the NO2 group, nitrobenzene. If we are able to form the di-substituted product under vigorous conditions, where will the substitution take place? At the ortho or the meta position? Absolutely, at the meta position. Same way, again, extreme conditions, trinitro product giving us trinitrobenzene. It will again be at the meta position. You know, interestingly, we can generate, if we carry out the same reaction, nitration of toluene, that's another alkyl derivative of benzene. Same conditions, concentrated HNO3, concentrated H2SO4. Yes, go on, write the conditions of the reaction and write the products. Go on, do it till step 3. So, first product, nitrotoluene. Second product, dinitrotoluene. Third product, trinitrotoluene, TNT. Interesting, what does TNT remind you of? But believe me, it's not so easy. Now coming to sulfonation, as we said, replacement by SO3H group. It's not easy. You know why it is not so easy? Because here you do replace by the SO3H group, but if the conditions of your reaction are dilute, that means if there is more of water in the solution, what will happen is this reaction has a tendency to go backward. In other words, you get more of benzene rather than the benzene sulfonic acid. So what do? Is we try to keep the reaction directed towards the right hand side by using a solution which has an excess of SO3, which we call as fuming sulfuric acid. Fuming sulfuric acid, even more active. So what happens over here is it is just like auto ionization of water. So the water can behave as an acid as well as a base, forming H3O positive and OH negative. Same way, molecule of H2SO4, one as an acid, one as a base, forming H2O, HSO4 negative and SO3H positive. So there we go, we have our electrophile, and this can form the substituted product in the benzene ring, causing us to give benzene sulfonic acid. Easy? Are you writing? Good. Next we go on to, are we done already? No. We have 2 more reactions to go. Friedel-Crafts reaction. Friedel-Crafts reaction are further of 2 types. Alkylation means when you replace the hydrogen by an alkyl group. Acylation means when you replace by the acyl group, acyl coming from the acid. So RCO group is the acyl group, right? So the catalyst for these reactions are again the Lewis acids, anhydrous aluminium chloride, BF3, SbCl5, FeCl3, SnCl4, ZnCl2, etc. List being unlimited. So would you like to write the products of Friedel-Crafts alkylation? So you treat the benzene molecule with an alkyl halide. I am writing only one catalyst in this reaction. You can go ahead and write the others, replacement by the alkyl group. Can you write the reaction to show the generation of the electrophile in this reaction? It's something similar to your, yes, go ahead, you've got a halogen over here. Very good, it's something similar to the halogenation. So we've got the alkyl derivative, correct? Go ahead, react with alcohol, positive, negative, complete the reaction. You've got an alkene. So what happens over here is, yes, in the first place it does remove the hydrogen, but it says, oh please, I'm short of one hydrogen, because this double bonded compound, you know, it is fond of extra atom. It wants to add an extra atom. So even though, so you can understand like this. So let us say in the first place it does become like this, but this carbon starts crying, oh, this is fully satisfied. What do? I still have a double bond to go. Is it possible that this carbon can form that many bonds, right? So what do? So the double bond here will convert to a single bond and a hydrogen becomes attached over here. So the double bond changing to a single bond. So we have CH2CH3, alkyl benzene. But you know, if these alkyl groups are big, 3 or 4 carbon atoms. Do you know rearrangement can take place? And have any idea about that? To explain that concept, I am just taking a very small example. The details we can do later as well. So, let's suppose I have got benzene and I want to substitute it by a butyl group. So, what do is I treat it with a halobutane. So, let us say chlorobutane, bromobutane, anything. What would I expect? Positive, negative, right? So, yes, very correct. So, positive will become attached to this carbon over here. So, what we will have is CH2, 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 CH3. This is what you would expect. But what do you actually observe is 60 to 80% of your solution is this. Oh my God, what is this? That's a phenyl derivative of butane. So, how do you explain that? You see, when the halogen atom goes off, so you've got a carbocation. We go on to our concept of what type of carbocation it is. The carbon, the positive carbon is attached to only one other carbon. So, this is a primary carbocation. Says, okay, the carbon which is positively charged, the carbon next to it says, okay boss, why don't you take a hydrogen from me and give me your positive charge. That way our plus is now sandwiched between 2 carbon atoms and we become a secondary carbocation, and the secondary carbocation is more stable, right? We will be more stable, and that's a interesting proposition, correct? So here we have a choice of primary carbocation and secondary carbocation, and secondary carbocation is any day the winner. So that means what do we have? It is this carbon which gets attached to the benzene ring and explains why we are having a secondary substituted product instead of a primary one. Acylation, replacement by an acyl group, positive, negative. Don't do the mistake of bonding through oxygen, because if you see the expanded structure of acyl chloride, CH3COCl, CH3 C double bond O Cl. So this is negative, this is positive. So it becomes attached at the positive ends, EOR. So what we could have is benzene. Would you like to write the reaction now? So this product that you formed is a ketone. Same way, form the product with acetyl chloride. So COCH3, acetophenone, correct? Please understand the difference when you are showing the bond through oxygen. You know, this is a very, very common mistake that I have seen the children doing. You see, what is this? This now becomes an ether. It is not a ketone. The bonding is taking place through oxygen. Oxygen is serving as the link between the benzene and the carbon, and that will not be correct. So here we've got the ketone. And what will be the side product? HCl. Go ahead, write the mechanism of this. Same way, instead of acetyl chloride, you could also take acetic anhydride, CH3CO, CH3COOH, OH. This is 2 molecules of acetic acid. Remove the water from it and bond the 2 molecules through the oxygen atom, and we will have what we call as acetic anhydride. Again, what will happen over here is we will get acetophenone CH3, and our side product will change. It will be CH3COOH. Correct? if we reduce this C double bond O, ketones can be reduced. You have Clemmensen reduction, Wolff-Kishner reduction. Don't panic, don't panic. You'll be learning all these later on. In fact, we've already made a mention of it. So this can actually be converted into CH2CH3 by reduction. So we could have something like this. So you can prepare alkyl derivatives of benzene using acylation as well, right? So you could have these reactions taking place using an acylation reaction or acyl chloride as well. So the question arises, what are you going to prefer, alkylation or acylation? As we have seen in the case of alkylation, when you have bigger alkyl groups, there could be rearrangement. So you don't get the expected product. Whereas in the case of acylation, what you can do is you can do the acylation followed by reduction in order to get the alkyl derivative, followed by reduction, right? And the second interesting part, when you're talking about alkylation, what happens is the ring now becomes activated. So it can undergo further substitution reactions. Whereas in the case of acylation, because of the C double bond OR group, what happens is this becomes electron withdrawing. So the ring is not happy to undergo further substitution reactions. So you can have a wider choice of products as to what you can form using acylation compared to what you can form using alkylation. So if you have a choice, you would definitely prefer acylation over alkylation. Lots for this lesson, right? You have learned so many new things, right? Must be tired. So many new concepts, so many new terms. Why don't you take a break? Relax, and then we will meet again for part 2, where we will be discussing more properties of benzene. See you soon.